In this video, we are going to talk about understanding 3D scanner accuracy. All right, let's get started and talk about why we made this video. The main reason is to help you make an informed decision. We find customers who are looking to purchase a 3D scanner, the more informed they are, the better decision they can make, and overall, the happier they're going to be with whatever equipment they buy. And the key to that is having good information. Now, some people will go out and do this research on their own, and others, just don't have the time or desire to do it. The other thing we're seeing out there in the market is a lot of misleading statements about accuracy. So I think they want you to assume certain things, and they just may not be true, or there's really more to what they're saying, and you should dig a little deeper. And that goes for standards as well. Standards can be interpreted differently. We're going to talk about that, or they can be left vague, and again, leave you to maybe assuming something that's maybe not quite true. And as I mentioned, there's a lot of information out there. Even when you do go out and inform yourself, sometimes it's confusing. So we're going to try to do this in a fairly quick summary of understanding 3D scanning accuracy and what you should look for. Okay, so here's what we're going to discuss. First thing we want to do is define accuracy. Okay, now we're going to try to keep this fairly high level. You could get down in the weeds on this stuff and spend a lot of time. But we're going to do all of this at a fairly high level to kind of get through this. Now, if you want to just jump to the end and, kind of get a summary of, what we think, and that's what we're calling the accuracy riddle, there's timestamps in the description below. If you want to skip all this stuff and just kind of see what the end results are and what we think, you can do that. But after talking about accuracy, we're going to talk about what affects accuracy. So what can keep things accurate or make things very inaccurate. We're going to talk about what ISO 17025 accreditation is. We're going to talk a little bit about what traceability is, because that's important. And that leads into a couple of standards, accredited standards. We're going to talk about ISO 10360 and VDI VDE 2634. And like I said, to wrap it up, we're going to kind of sum this all up and basically tell you what you need to know when purchasing a 3D scanner. Okay, so what is accuracy? Okay, what does that mean? So what accuracy means is the difference between the measurement taken and the true value. Okay, so that difference, how accurate it is. If you're aiming for the center of that target, how accurate are you in hitting that center of the target? Precision is the variation of measurements on the same part repeatedly measured with the same device. So again, if you're aiming at the center of the target and you're consistently hitting, let's say off to the left, like you see here in the sample, that's very precise, but it's inaccurate, okay? So there's many factors that affect accuracy and precision. So ultimately what you want is a device that is not only accurate, but it's precise, meaning repeatability. You can take a measurement, you can get a very accurate result, and you can do it over and over again. And this is validated through accredited test results, which we will talk about. And that system is calibrated to traceable artifacts. So that's really a summary of what accuracy is. It's the combination of being able to measure something accurately, with the right result, and do it over and over, basically that repeatability. All right, let's talk a little bit about what affects accuracy, because you can have the most, accurate system in the world, but there are things that are going to affect it. So starting out, certainly the equipment itself, right? How accurate is it to begin with? Now we'll get into how that's all defined here in a bit, but when you buy a piece of equipment, how is it manufactured? What is the build quality like? How was it calibrated? How it's designed? How it's assembled? The components themselves all play into the accuracy. If it's not manufactured well and it's poor build quality, you're probably not going to have good accuracy to begin with. But there are other factors. As I mentioned, environment is one of the biggest. For example, temperature or vibration, wind, humidity, those can all play a role when you're trying to measure something. Another big factor is the human factor, and that's the operator's skill set. Does he know how to operate the equipment properly? What is the size of the part? We're going to talk about this more later because you may see accuracy statements for a 3D scanner, but you're measuring things that are far bigger than the accuracy statement as far as like what they measured to. So if they measured a 3-inch gauge block and you're scanning parts that are 20 foot long, you are not going to get that accuracy. So part size plays into it. Surface conditions, especially with 3D scanners, whether it's structured light or laser, surface conditions can absolutely affect the accuracy of the scanner. Another thing is part stability. Is the part rigid? Is it being held in a way that it's not moving around? Does it need to be fixtured? Or is the part non-rigid, something flexible or flimsy? It's going to be very hard to measure that part if it's moving around because it's just thin or something like that. Another thing is tool wear. Now, this typically is going to be for like a laser tracker or some kind of probing system, like an articulated arm or an optical probing system. If your probe or your SMR, if that tip is worn down or uneven or not round anymore, those things wear. So you would get improper measurements. And then lastly, just the measurement method. If you're measuring certain things, are you even doing it right? Are you doing the right commands in the software or the right methods to get the correct measurement? So those are some of the big factors that come into play. So again, it could be poor equipment right out of the get-go, or it could be some other factors that affect the actual accuracy. All right, so what is ISO 17025? So what that means, if you see a manufacturer of 3D scanning equipment and it says, ISO 17025 accredited lab, that means that they have the technical competence in performing measurement tests and calibrations. So if you're going to send your equipment back to a manufacturer to get recalibrated, typically on an annual basis, or if it has to go in for repairs, you want to know if they are an accredited lab to be able to do that. And that means they have the proper equipment, they have controlled environments, lots of different things to perform their tests. They have some kind of quality management system, typically similar to like an ISO 9001, but specifically tailored for lab operations. They have traceability, which we'll talk about in more detail, but basically the equipment they're using to recalibrate your equipment is traceable back to, typically in the US, it's a NIST standard, but there's others out there. We'll talk about that, and that they are globally recognized. So those are some of the things. So if you're buying a scanner from a company that is not an ISO 17025 accredited lab, and they are going to be calibrating your equipment, that's a big red flag. You really want somebody that has this accreditation. Otherwise, you just don't really know how they're doing it and what they're doing. So I mentioned traceability. So what does that mean? So that means, going back to kind of the 17025 accredited lab, the equipment they use in their calibration process is measured to a traceable artifact, okay? So I'd mentioned NIST, usually in the US or North America. NIST is one of the most popular, but there are other labs and metrology places out there like NIST. But basically, they are going to measure an artifact and certify it. So the 3D scanner manufacturer will have various artifacts. They could be ball bars. They could be different plates. There's all different stuff. You could spend all day talking about all these traceable artifacts. But to keep it simple, it might be spheres. It could be ring gauges. It could be ball bars, etc. They are sent into one of these facilities and they are measured and calibrated. So they put a date on it and they put all those measurements. Now, NIST has a really good video, and I'll put the link in the description below. The picture you see here is their CMM. It is insane how accurate this CMM is and all the things they have done over the years to make this thing super accurate. And it has a lot more to do than just the machine itself. It has everything to do with software and the environment and everything else. So it's about a 10-minute video, I think. If you really want to nerd out, I would encourage you to watch that. It's absolutely phenomenal. So a manufacturer would send in artifacts. NIST will then certify, basically measure them and tell them, here it is, and send it back to them. So then when you send your equipment in to be calibrated, they are going to use that artifact and measure your system to it. So that traces all the way back to NIST in this case, okay? So that's what a traceable artifact is. If you're getting your equipment not calibrated to a traceable artifact, I would just be careful. I'm not saying it's the end of the world, but it's really, if you're trying to do precision metrology, it's really kind of important you do that. If you're not doing hardcore metrology, maybe it's not as important. You definitely want it measured to an artifact, but you really want to look at where you can trace that artifact back to, okay? So that's what traceability means. Okay, so now let's get into some of the standards, and this is where you can dig really, really deep, okay? Now, there are different standards out there. I'm gonna concentrate on the two most common ones referred to for 3D scanners, or really CMMs in this case. So ISO 10360, there's some other standards out there. Some of them are being phased out, and this is kind of becoming a bigger standard. Now, let me explain something, okay? So it's a series of standards that specify performance requirements for different types of measurement machines. Primarily, historically, it's been all around CMMs. And it's broken down into different parts. So one of the gotchas here is people will say, it's accurate, and they put some accuracy statement, and they will say to ISO 10360. Well, that doesn't really mean anything, okay? Because you have to refer to what part, okay? So for example, part 1 is just definitions. Part 2 is a CMM. A CMM is a coordinate measuring machine measuring linear dimensions. And then there's probing performance to discrete points. And then there's a scanning measurement mode. And CMMs have multi-point or multi-probing stylus. So it looks like kind of almost T-shaped, where it has multiple tips on it. And then there's computational estimation. There is, you can mount a laser scanner or structured light scanner on the end of a CMM. So those first 8 parts are all around CMMs, okay? Now, part 9 is for laser trackers. And I'm not going to go into a lot of detail on all this different equipment. Laser tracker is more like a portable CMM that uses that SMR I referred to. And then articulating arm is, basically an arm articulating with a probe on it or a scan head. And then there's a part 13, which people sometimes reference. This is for optical 3D CMMs with a structured light or laser scanner or for freeform surfaces. But the standard specifically says it's not for laser trackers, it's not for articulating arms, it's not for CT scanners, and it is not for handheld laser line scanners, okay? So, it's not meant for these things. So we'll talk more about this. But when people say, it's ISO 10360, in and of itself, that doesn't mean anything. As you see in the pictures, there's different parts. And when you get your CMM calibrated, they will use different artifacts and different measuring methods to, calibrate that system to these different parts. So this is one of the most confusing things out there is people just use this general ISO 10360 and it kind of doesn't mean anything. You really got to dig in and understand more about it. So to take this a little further, there's a statement in ISO 10360 part 13 that the acceptance and re-verification tests are applicable only to Cartesian, that means XYZ, CMM, so that's like a table-based, CMM, a traditional CMM, with optical distance sensors. While it does not explicitly apply to non-Cartesian CMMs, that would be a tracker, a handheld scanner, an articulating arm, the parties may apply ISO 10368, and 2013 is the latest update to that standard, to non-Cartesian CMMs by mutual agreement. Okay, and so what does mutual agreement mean? Well, is there a mutual agreement out there among these other manufacturers? The short answer is I don't think so. right? But they're basically saying you can use this standard, and some people do, and they will reference it. And we're going to get into this a little bit more, but you really want to look at, okay, what exactly are they measuring it? How are they doing it? If they're referencing ISO 10360 part 13 or part 8 or whatever part, you want to take a look at what they're actually doing and how they're doing it. All right, so let's talk about VDI VDE. Now, VDI VDE, part 3 specifically, is a German standard for optical 3D measuring systems, multiple view systems based on area scanning. Part 3 establishes standardized procedures for evaluating the accuracy and performance of optical 3D measurement systems. So what that means is systems like a structured light scanner that may mount on a tripod and then you move it around, or maybe the part rotates, or a handheld scanner where you're continuously moving around and scanning. So this standard came out in 2008. A lot of structured light scanners came out of Germany in the 90s and 2000s. So they came up with this standard because there wasn't one. And technically, there still isn't one. So this is the best standard for these types of scanners. Okay. So it measures things like probing error. That's the measuring a series of different size spheres. It measures the spacing between the spheres. And then it measures length, basically, 2 points to any 2 given points. So as of today, this is the best standard and probably the most referred to in the world of portable, metrology, portable 3D scanners, structured light, or laser-based scanners. You'll see most of the high-end manufacturers are going to reference this standard. We'll get more into what those results look like, but this is the most common you're going to see out there. So that brings us to what I call the accuracy riddle, because it really is a riddle sometimes. You're given information and you got to try to figure it out. And I think a lot of times that's by design so that you are confused, you don't really look into it, whatever it may be. So let's talk about this a little more. So when you're looking at a 3D scanner, you want to know what standard is it measured to, okay? And if it's an accredited standard, it's going to be one of them that I've mentioned, or it may be another one, but those are the two most common. And if it's just some stated accuracy, then I would be very cautious of that, because you don't understand stated. What does that mean, right? It's not an accredited standard. It's not a standard that industry and people have agreed to and use. Stated could really mean anything. Now, like I said, if it's an accredited, to what standard? Is it the ISO? Is it VDI, VDE, or is it something else? What standard what accredited standard are you referencing? And again, if it's not accredited or just stated, then to what, right? And that also goes back to the ISO 17025. If it is just a stated accuracy and they are not an accredited lab, I just wouldn't hold a lot of value in any statements they're putting out there, because you just don't know unless they're willing to share in detail how it's being done. So as we talked about ISO 10360, there is not a specific standard for handheld scanners, but people are using different parts of it. And that's fine, as long as they're telling you what they're measuring, how they're measuring, what the results are. Okay. I'll dig into this a little deeper in a minute. And then the VDI VDE 2634 part 3, that is explicit to non-contact portable scanners. It's a pretty good standard out there. It's pretty widely accepted by most people, for portable 3D scanners. But you also got to look at those measurements, and we'll go into that here in a little bit. But you got to look at the actual measurements and the setup. Okay, because the other thing you've got to look at is tolerance stack up. Okay, and what is that? That is accuracy over distance. So you'll get an accredited measurements off of something, but that's going to be within a certain range, a certain distance. What happens when you're scanning parts bigger than that? So if it's calibrated and measured to let's say a ball bar or something at, let's say, a 1 or 2 or 3 foot distance, or a 4-inch gauge block, well, it's accurate in that volume. But what about beyond that? Okay. So, that's where you get into this tolerance stack up. We'll talk a little bit more about that in a bit. And does the scanner provide artifacts or photogrammetry to improve this accuracy over distance? And how is that measured? Okay, so if you're doing larger stuff, this becomes more important. If you're doing smaller stuff, it's not a big of a deal because those standards are usually within a volume that handle a lot of parts. But if you're doing stuff bigger than that, then you got to look at this. And that's why I'm saying you need to look at what they're measuring, how they're measuring it, what size artifacts are these, what size spheres, whatever it may be. You've got to take a look at that. So another thing is what I feel is kind of misleading is statements that say up to. So there's MPE versus up to accuracy statements. So when you're looking at somebody's accuracy statement, MPE is maximum permissive error, which basically means the worst case scenario in any given test. Okay. So if you measure something 5 times and the worst case is this value, that's the accuracy statement. Okay. Up to, well, what does that mean? If you measured something 5 times and your best measurement was this, but the rest of them were way out, then it's not reliable and it's probably not repeatable and usually not accredited. And I don't think it can be trusted. I think it's very misleading to do up to, right? Because you're just not given a lot of information. Up to doesn't mean repeatable usually. So they measured something a bunch of times. Hey, this was our best measurement. Let's go with that. So I would avoid anything that uses that kind of language. Also avoid any scanners that say no calibration required. If you're not calibrating your equipment every time you use it, you're not using metrology equipment. There's no way. You want traceability. Typically, when we're doing inspections, we're saving the calibration report. And sometimes we're doing measurements, not only calibrating the equipment, but then measuring it to traceable artifacts and including that in our report so that there is no doubt that our equipment is accurate. Okay. And, and also does your scanner monitor things like temperature, right? So there's all kinds of things in there that you've got to look at. But when I see things like up to, I think that's just very questionable. And then the last thing you'll see sometimes is level of uncertainty. So what is that? So that's just kind of some of the unknowns, right? So any inaccuracies back to the traceable artifact, it could be in there because, you just don't know what is perfect, what is accurate, right? And then, as we mentioned, over distance. So when you see those stacking tolerances, there's some uncertainty there because, again, you just don't know. So that has to be factored into your accuracy statement as well. So let's walk through an actual calibration certificate. So it's got the name of the product. It's got, where, who manufactured it, serial number, when it was done. And then we get into the acceptance test procedure. In this case, it's the VDI VDE standard, part 3 we talked about. Then it talks about how it was done. So 5 ball bars, 3 different lengths, how they're positioned, all that kind of stuff. Then it's got the results from those tests, whether it passed or not, and the individual ball bars that you see here, the different lengths, 650, 520, etc. So now you'll also notice that these, I'll talk more about this, but the results are better than the accuracy that the manufacturer puts out. And that gets back to that uncertainty a little bit, right? What is the difference between the uncertainty of the original artifact measured and then the machine that the actual calibration is done on, and then other factors. So that accuracy number that they put out are usually higher or worse, depending on how you want to look at that, than the actual calibration results, right? So you got to factor that uncertainty into a number you're going to put out there because you've got to live with that number. So keep that in mind. So here on the second page is the positions in the volume for the probing size error. So it's kind of a 3D volumetric picture you see here. That's where the locations are of each one of those. So here are the actual measurements. So measuring that size error, basically the diameter of the spheres on that ball bar in all those different positions. And so you see the actual amounts there on the top, and then below you see a graph. And then in red, you see the stated accuracy from the manufacturer. So you can see the deviation is well under that stated accuracy. So could you do better than the stated accuracy? Yes, but the manufacturer is going to guarantee it, so to speak, at that, the accuracy they put out there. And again, that gets to a little bit of that uncertainty and repeatability, right? Because you do have a little bit of variance there. So, you want a number that you're comfortable with. Next is the sphere spacing error. That's basically the distance from ball to ball. And again, the key thing here is it's a volumetric measurement. Those ball bars in this VDI VDE test are spaced out in a 3D volume. You can see up, down, across, etc. And then they're 3D scanned and measured that length. That's a true volumetric accuracy statement. You don't want just one ball bar sitting on a table where you kind of measure back and forth. In the real world, you're scanning 3D objects. You want your accuracy statements to reflect the same thing. This shows those actual deviation values for each one of those, whether they passed or not. And then finally, here it is on the chart. And if you look, what is the worst measurement in this case? It's the XY1. That's the one that kind of goes across the volume on an angle. That's typically the toughest measurement to make because you're measuring in length, width, and height. Scanners can be very good in one direction or the other, but to be good in all three directions is a key test. So this gives you a visual representation of those measurements and the accuracy statement made by the manufacturer. Okay, so to wrap this up, bottom line is if you're going to look at purchasing a 3D scanner, or maybe just somebody that's going to come in and do some measuring for you, you really should do your homework a little bit. So if you're going to get a demo, during the demo, have them measure an artifact, make them prove it to you. We have ball bars, we have in cases, we travel with them, and we use them on real jobs when we're out doing work. We will pull it out, we will scan it, and look at the results and make sure our equipment is up to snuff. Ask to see an actual calibration report. Our better customers, our smart customers who've been doing this a long time, maybe they already own CMMs, they will ask, show me a calibration report for this equipment. And just like we went through, they're going to look at it and they're going to look at how it was done and what the results are. Understanding that uncertainty and stacking error is important. Okay. When you start doing larger parts, you are not going to get the accuracy stated by the manufacturer, even under an accredited test. It's just not going to be that accurate that far out. Some companies do gauge R&R reports. We've done our own on our equipment. I'm not going to get in the weeds on that, but that's basically multiple users, multiple scanners. You're basically testing out, kind of doing your own accuracy test with some variables in there and seeing what results you get. Okay. So trust but verify. Don't just take the manufacturer's word, especially when they're very vague. If they're not going to show you a calibration report, if it's not done to an accredited standard, things like that, I wouldn't put a lot of stock into what they're saying. Another important thing is where is the 3D scanner manufactured? Because we're seeing a lot of scanners that aren't necessarily made by the company representing it, and it may be made elsewhere. Now, what does that mean? So if you have to follow any kind of ITAR, EAR, DFARS, or CMMC regulations on hardware and software, where that scanner is manufactured is going to be very important. Okay, so just because the company may reside in one place doesn't mean that the scanner they're trying to sell you was manufactured in that country. So you need to look at this. This is really important if you're doing any kind of defense work, DoD type work, government work, aerospace work, others. Does the equipment and software meet these regulations? You really need to look into this, because if it doesn't and you're using it that could cause you some issues. So you should know where your scanner is manufactured, not what the label says on it. Another thing, when you have to send it back for calibration, where is it going? How long is it going to take to get it back? So these are kind of just some things related to that. So once again, do your homework, trust but verify, take a good look before you spend a lot of money on equipment. Does it really meet the statements that a company is making about that equipment? So hopefully you found this video helpful. We could go into a lot more detail and make this video, hours and hours long, but I want to give you a good overview so you kind of understand it. Hopefully this is enough information so that when you go out and buy something, you know what you're looking at, or if somebody's going to come in and do services for you. Now, if you have any questions about any of this, feel free to give us a call. Happy to answer any questions. If you're interested in a 3D scanner or a laser tracker or long range scanner, whatever it may be, we can help you out. Feel free to give us a call at 877-845-2700, or you can email us at info@ems3d.com.